I always have to focus for a second there. Suppose I have an object moving at a constant speed, and its position is described by a function r of t. We know that its velocity, then, I can find by taking a derivative, r prime of t. And the speed is the magnitude of the velocity. Suppose my object is moving at constant speed. Well, here's the speed. And we're going to assume that that's constant. Something that we know about a magnitude of a vector is equal to its dot product with itself. Now I want to take a derivative, both sides here. So the derivative of the speed is, well, the derivative of a constant is 0. And here I have a dot product of the velocity. Well, I'm going to need the product rule for that. So I have r double prime times r prime, and then the other way around. Well, so what have I discovered here? This is two of the same thing. This says that the second derivative of r, its acceleration, when I do a dot product with the first derivative of the velocity, I get 0. Well, when the dot product is 0, that means I have two things that are orthogonal. So if I have an object moving at constant speed, the direction of the acceleration is orthogonal to the direction of the velocity. Suppose I have something moving in a circle. The direction of the velocity is tangent to that circle. The direction of the acceleration is toward the center of the circle. So velocity and acceleration are perpendicular when my object is moving at constant speed. But what if it's not? What if it's not is the case if I have projectile motion? My projectile is moving in some curve. The velocity is not necessarily perpendicular to the direction of the motion. The acceleration. The acceleration is due to gravity, and that's toward the ground, no matter where the object is. However, so I have my velocity here, my acceleration toward the ground. Something I can do is take the acceleration and break it into two component parts, one of which is in the direction of the tangent vector, in the direction of the velocity, and the other of which is normal to that. So my tangent vector t up here, my normal vector to the curve here, and I can take that acceleration and divide it into pieces that are in the same direction as the tangent vector and in the same direction as the normal vector. This is job for a vector projection. So this is going to apply when my object is not necessarily moving at a constant speed. These two components we're going to call the tangential and normal components of acceleration, hence the title at the top. So what we just said is I can take the acceleration and break it into a part that's in the same direction as the tangent vector, and a part that's in the same direction as the normal vector to the curve at the point that I'm looking at. So these tangential and normal components of acceleration are scalars multiplied by the tangent and normal vectors respectively. Well, so certainly we can say the tangential component of acceleration is the magnitude of the projection onto the tangent vector of the acceleration vector. And that's true, but it's not necessarily convenient. We also know how to do this. This is the dot product of A with T divided by the magnitude of T. We went through a lot to try and get T when we were finding unit tangent vectors. So it would be really nice instead of this to have something that's in terms of my original function, r of t, and possibly its derivatives instead of this tangent vector t. Well, the first piece of good news here is the magnitude of t. We set up t to be a unit tangent vector. So its magnitude is 1. Which means I'm down to a dot t. But also, the unit tangent vector was the derivative of my original function, which we could call its velocity, and it's a unit vector. So we're dividing by the magnitude. And we might as well go like that. But in terms of our original function, acceleration is the second derivative, and velocity is the first derivative. So this is r prime dot r double prime divided by the magnitude of r prime. So the dot product of the velocity with the acceleration divided by the magnitude of the velocity. And that's the tangential component of acceleration. For the normal component, we could subtract. We could try. Might be messy. And it also might be convenient to be able to find it in its own right and not have to go through finding the tangential component first. So I'm going to come back to this thing that we said. The acceleration consists of a tangential component and a normal component. I'm just going to observe that t, this unit tangent vector, is the first derivative divided by its magnitude, like that, which means I can rewrite v as t times the magnitude of v, and that's going to be really convenient in a second. Let's see, I want to take a cross product of the acceleration with the velocity. Here we go. I got v cross a. And so that means I'm going to do a cross product v with each of these. So I got at times t and an times n. But t is v is t times the magnitude of v. So let's make that substitution here for v. At is a scalar. I'm going to pull that out. Magnitude of v. And then I have the t that was already there and the t that came from the velocity vector. And we'll do the same thing in the other half. Here's the next piece of good news. When I do a cross product of a vector with itself, I get 0. So this whole mess at the beginning, gone. And I'm down to V cross A is the normal component of the acceleration, which is what we really want. We're aiming for AN here, times the magnitude of the velocity, and then the cross product of the tangent vector and the normal vector. Let's find a magnitude. We'll take magnitude on both sides. If my vectors are equal, their magnitudes are also equal. This AN, the normal component of acceleration, is a scalar, so I'm taking its magnitude as just itself. The magnitude of V is already magnitude, so I just need the magnitude of T cross N. We have one more piece of good news. T and N are both unit vectors, which means the magnitude of T cross N is 1. So this means we're almost there. I have AN equals the magnitude of V cross A divided by the magnitude of V. In terms of our original function, which was R, way back on the other page, the velocity is the first derivative of my function, acceleration is the second, divided by magnitude of R prime. So normal component of acceleration and tangential component of acceleration.